Hey everyone, this is MAT 125. We're in Unit 4, Block 2. We're in our last video. This is video number 5 for this block. We're looking at the lecture guide, example number 9. It says, suppose you're given this derivative function, and it says below is a sketch of the graph of this function from 0 to 60. And it's asking us to shade in the region of the graph that represents the definite integral from 0 to 60. Now remember, the area between the curve and the x-axis is what that definite integral will be. So let's shade in these regions. So the regions would look something like this. So here's this first region, and these tick marks look like they're going from 10, 20, 30, 40, 50, and 60. Part B says, if we know that these particular values are given, that there's intercepts shown, the first intercept is at 22.2491, and the second intercept is right here at 49.5389. And it turns out that these values are given, that in this definite integral, here is the value, in this definite integral, here is the value, and in this definite integral, here is the value. Label this graph with our x-intercepts and our definite integral values. So when we do, we get this. Here's my intercept values. Here's that intercept of that we found, the first intercept. Here's the second intercept we found. This is the region that is the definite integral from 0 to that first intercept. This is the definite integral, that shaded region, which makes sense that it's negative because it's below the x-axis. And here's the shaded region for that second intercept till 60. Okay, so part C says, use the values that were given to give us the value of this definite integral. Well, that would be simple. We would simply add those values together. So the definite integral from 0 to 60 of that function is going to be equal to each one of those parts added together, and we are going to take into account that this was a negative value, so we're going to add them all together, and I get 57,000.002. All right, part D says, okay, now can you approximate the value of this definite integral by using 600 rectangles in Excel? Use Excel to do the left sum, the right sum, and what we did in the past, that template we used in the past, to come up with a way to find the approximation for this using Excel. Now this is definitely a tool you're going to need for your final exam, so make sure you know how to do this. So let's go to Excel to look at how we would do this. All right, so now I'm in Excel, and I tried to save myself a little bit of time by typing the value of x and actually the value of the formula that we had there that was given to us in example 9. So I typed in that formula. Now it asked us to make 600 rectangles. So remember, in order to use 600 rectangles, we have to look at the interval. We're looking at the interval from 0 to 60. So we do b minus a, which is 60 minus 0, divided by how many rectangles I want to draw, which is 600 rectangles. That means I want to measure every 0.1 units. Now, what I did here in is Excel, you can have Excel do that calculation for you. You do 60 minus 0, which is 60 divided by 600, which gives you 0.01. So what we're going to do here is we're going to go into Excel and use our fill feature, as we've done many times in the past. And we're going to fill this column up, but we're going to have it fill it by going up by 0.1, and we want it to stop at 60. And then I already have the formula typed in there, so I'm just going to click on this to get, here's my value that I would get. So this is an easy way to have Excel fill in. You can see that's a huge table, 600 rectangles. You can see how long that table is. Now, let's talk about finding the LRAM and the RRAM. Remember, the LRAM, or the left-handed rectangular approximation, is found by the width of each rectangle, which we just found up here. That's the 0.01. So we're going to always do that first. The width of the rectangle is 0.01 times the sum, and we're going to take the sum of the first value, and we could hold this down and scroll all the way down, but this is a pretty long table. So what we do is I'm going to put a colon here, and then I'm going to go in and just look at what is my almost last value here. I'm sorry, I went too far. So my almost last value, so we're going to take everything in our table except for the last one, which is that value right there. And you notice how Excel will fill in, okay, you want to take all those values. Notice you can see it takes in all those values. So that was the 601st value from my table. And I'm going to close my parentheses here. So this will give me my LRAM. It's going to take me my width, which is 0.01, times the sum of all of those lengths. The first length being 5,000, second length being this, and obviously we're not going to draw 600 rectangles. And then we hit enter, and then we do the RRAM. That's going to equal 0.01, which is our width, times the sum. And in this one, if I'm going to take an RRAM, I want to take the last value up until this value. So I'm going to start with not the first value, but the second value, and then a colon. And I think we're at the 601st. Let me just make sure. 602 should be my next value, I think, on my value of my table. I'm sorry. B of 602. Let's just make sure it has what I want it to do. I want it to go all the way to the end of the value. Now I could have just scrolled down here and clicked on that value, but I remembered it was the 602nd value. Just remember to write B there. All right, so then we know that a good approximation will be the average of those two. Now this is another thing we can use in Excel. So here in our PowerPoint, we went to Excel and we found those values. The values were 56,806, 57,196, and then the overall estimate of the two was the average of the two, which was the 57,001. All right, let's go on to problem 10 in your lecture guide. This is on the basis of data obtained from a preliminary report of a geological survey team. It is estimated for the first 10 years of production, a certain oil well can be expected to produce at a rate of this B prime. Again, this is a rate of change, so this is a derivative function, where T is the number of years after production begins, and B prime of T is measured in thousands of barrels per year. And remember, again, that makes sense to us because the derivative function should be a rate of change. It should be thousands of barrels per year, or that should be a fraction, and it is. All right, so it says first we want to estimate the yield during the first 10 years of production using 200 rectangles. So we're going to go back and use Excel again. What's really nice about Excel here is if we were going to use the fundamental theorem of calculus, we don't have an easy way. We actually don't have any way to go backwards from the product rule. We don't have a way to go backwards here. So the only way that we can do this, we can't use the fundamental theorem of calculus. We would have to use Excel here to approximate this. And this is what often happens in real life. We don't get a nice function that we can go backwards from with a rate of change. So we use Excel to give a good approximation of the overall accumulated amount of change. So let me pause here and go to Excel. All right, so now I'm in Excel. And the first thing we always have to figure out is how often we're going to measure our t-value here. So it said to use 200 rectangles in 10 years. So if you think of this, the interval is from 0 to 10. So it would be b minus a, which is 10 minus 0, divided by how many rectangles I want to do is 200. So that gives me 0.05 is how often my t-values have to measure here, my width of each rectangle. And again, I did this in Excel. I just had 10 divided by 200 to get that value there. And then we go back over here and we're going to again use our autofill, which is the greatest feature here. We don't have to do much work here as far as typing. We want this to happen every 0.5 units and we want to stop at 10. And again, Excel fills that whole table in for us. Here, I already put the formula in, so I would save some time here. So I had the formula in here. So there's my formula for the value of the derivative over those 10 units. And again, this is a huge table. You can see it's a really large table. So let's do our LRAM and our RRAM. The LRAM is always equal to the width of each rectangle, which in this case was 0.05, multiplied by the sum, and the LRAM is always the first value, colon, and then we're going to go down here and we're going to take everything except for the last value. So the next to last value right there, that's the LRAM. And then we're just going to close my parentheses. There's my LRAM. My right rectangular approximation is going to be 0.05. That's my width of my rectangle times the sum. And in this case, we don't take the first value, we take the next value a little bit, the second value there, and then all the way down, and I forget what value it was, so I'll just click on it, to the last value. Close your parentheses. So it's taking, here's your lengths times your widths of each one of those rectangles. And again, the average of this, we simply use. So those are our values that we got for each one of those values. Here's the definite integral. There's our definite integral. And it says in a complete sentence, interpret what this means. What did we just find? We just found that in the first 10 years of oil production, the well produced 12,397 barrels of oil, 0.5221 barrels of oil.